You please run it for R load, RL load, RLE load. Okay, you please run it.
Yes, for R load.
How much firing angle you have chosen?
60 degrees.
60 degree. Okay.
Yes.
Achha, then one by one, show me the gate pulse. Then one by one.
Input voltage. This is output voltage.
Achha.
Output current.
Output current. How much current value? Okay.
Yes. For RL load, this output voltage. And output currents. For RLE loads.
Now you do one thing. You are taking for 60 degree. Am I right?
Yes, sir.
अच्छा, show me that zoom करो थोड़ा RLE load का थोड़ा zoom करो. Please zoom it.
Which one, sir?
RLE load, that voltage waveform, voltage and current.
Yes.
How much E value you have chosen?
It is 40, sir. Is it 40? Sir.
40. Sir, you please change the firing pulse.
How much, sir?
Change the firing pulse.
To 30 degree.
Now this is 30 degree. Na? You change it first 120 degree.
Yes.
No. Why this type of things are coming? Y-axis zooming, sir. Why? What you are doing?
It is not coming in this voltage range. That's why I'm
No. There is a Y-axis zooming option is there, na? Zoom karo Y-axis. Upper one, that plus sign is there. Can you see that plus sign? Y-axis zoom is there, na?
I'm not getting, sir.
Y-axis
auto zoom कर ले, auto zoom पे.
Okay. Yes. It's coming like this.
I'm not able to see actually. Okay, show me your report.
Yes.
Can you please make it full screen? Just for a moment. I'm just closing all those things. So, okay. Now it is properly. So that is so first page में जाओ. Go to your first page. धीरे scroll down करो. अच्छा, a analysis of Analysis of single phase asymmetrical and symmetrical semi-converter by using different loads. Okay, so R load, RL load, RLA load. Okay, scroll down karo. So you were doing, so you are using left alignment. Justified manner you can use. Okay. No, the theory portion. Scroll down karo. Scroll down karo.
Yes.
That should be justified. Scroll down karo. You didn't write any mathematical equations?
Yes, sir. There's.
Okay. Wait here. Okay, so you are
Yes.
changing that R value.
Yes, sir.
So other parameters you have not, many other columns you have not considered for power input column.
No, sir. I will add it, sir.
Power input and current. Okay, input current.
Current is there, sir. Current
This is
input.
IN is there. Okay. IN is there, I out is there. Okay. Power output, V calculations. Actual V out is there, no? 66. That's good.
Yes.
P out, P in. Okay, you please
Yes.
add both of them. Then you.
I have calculated, but I have not added, sir. That's why efficiency is there, sir.
That you please add. Okay.
Okay, sir.
Yeah, please add. So efficiency is 49%. Okay. Variations of R. Okay. Wait. Efficiency plottings are there.
Yes.
Acha. Okay, that range is varying 49 to up to 50%, more or less. Okay. More or less. Okay, so how much sample? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 samples are there. Very good. Acha, scroll down karo. Acha, that voltage and current plotting you also please include. Okay.
Yes, sir. There's
No,
voltage.
no. This is curve wavefrom is there. Scroll down karo.
Yes.
That Excel file plottings are there, na? So you are
Okay, sir.
pressing only changing of resistance, that efficiency you have only given. So better you do it additional to one is output voltage and output current. Okay. So
Okay, sir.
variation of R, you can understand that voltage is increasing or decreasing, or current is increasing or decreasing. That's why I am telling you. Okay.
Okay, sir.
So you can understand about that process. Okay.
Okay, sir.
Good. चलो scroll down करो.
For firing angles.
Firing angle. Let me see the changing of firing angle.
Yes.
So in degree, na 0, 15. 0 means uncontrolled. Okay.
Uncontrolled.
15 degree you have changes only. 15, 60. Scroll down करो. Okay, 90, 120, 150. Good, very good. So you
180 I
can
will
add
add, sir.
both the column. Okay. चलो और एक बार I want to see your table once. Okay. Scroll up करो.
Yes.
Changing of firing. Wait. Percentage I need to see. Okay, percentage is an error. Almost voltage and V out are almost same. Okay, calculated and calculator will be quite high. Okay, so error is okay within the tolerable range below 2%. Okay, then efficiency increasing of firing angles means efficiency is reducing. Why efficiency is reducing? Turn of time is reduced.
Increasing.
And turn on
Reducing.
time is reducing. Okay, that's why.
Yes.
The 60-degree efficiency almost 50%. Okay. And you can see the current value also decreasing, increasing
Decreasing.
of here. So
But
you can see around almost discontinuous conduction mode it can go. Okay, good. This is average current. Okay. So from the
yes.
figure you can see that some discontinuous portion you can see. This is average current. That's why you can see. I think scroll down karo aur ek baar. Please scroll down it. Current is almost okay. Achha, do you have the plotting with you? Plotting.
No, sir. I will plot it, sir.
So
I'm doing that now.
what you will plot? Okay, so varying of the firing pulse, efficiency, output voltage, and output current. Three
Output
plotting.
current.
Okay.
Okay. Okay, sir.
Okay, good job, good effort. चलो हाँ scroll down करो.
For RL also, for small value of inductance.
अच्छा, small value of inductance. Okay.
Yes. This one. For large value of inductance, 0.1 Henry.
अच्छा. Still, 0.1 is not very large value of inductor, very large value. Okay. So
After that,
no need to write the small value of inductance, large value of inductance. Okay, you write that inductance sample. Okay. No
okay,
need to
sir.
write that small value, large value. Okay. So large value is how to know that is large value. Okay. How to know that is
Yes.
small value. Okay. So no need to specify it. Okay. Only inductance. Only inductance value. Okay. Inductance value L equal to 0. Okay. So no need to specify small value, large value. Actually, 0.1 Henry is not large value. Okay.
Okay, sir.
I know that in material I have provided, it was written there the small value, large value. That is mistake. Okay.
Okay.
Scroll down करो.
For RLE loads.
Okay. You please complete the plotting. Okay. So plotting.
Okay, sir.
Okay. You please make it.
Okay.
So E value did you change for RLE load? E value?
No, sir.
Okay.
I will
Okay.
do that.
If possible, you please add it so you can
Okay,
also
sir.
understand. Okay. Good job. Good job. Good effort. Okay.
Okay.
Good. What's your roll number?
300.
300 na? Harsh Kumar.
Yes.
Okay. Now who want to show their simulation? Hmm?
Excuse me, sir.
Tell me, Ayushman, Amshuman.
Yes, sir. I have not done the report, but can you see my simulation files?
Show me, no problem.
Yes, sir. I'm sharing the screen. Is it
Yes, it is
visible now?
coming. Yes, it is coming.
Sir, as I said, I have done in MATLAB, and as instructed, I have found out use the mean, the average value block, and the RMS blocks for the current and the voltage itself. And
Okay.
this is for the R load, and
Hmm.
the voltage source, it is I'm having the peak voltage as hundreds and omega t,
Hmm.
and apart from that, the resistance value is 10 ohms,
Hmm.
and then the gate firing pulse, I'm having the pulse width as 5% of the total period and 30 degree.
Yes.
And the
Yes. Yes.
second is 210 degree, means 30 plus 180.
Okay.
So, and from that, I am getting this type of graph.
So, Anshuman, my just one
Yes, sir.
suggestion, when you are doing your simulation, so that observation table, if you do simultaneously,
Yes, sir. Yes, sir. I get it, sir. Yes, sir.
so we can also see that how much variations are there, and actually how do I get it that okay, from the pattern we can understand, but the
Yes, sir.
accuracy of the simulation we can understand from your observation table. Okay,
Yes, sir. Yes, sir.
observation at least if you have the simulation and if you have the simulation, so side by side. Okay, suppose
Yes,
one
sir.
R load you have completed the simulation. So if you prepare the observation table with R load, so one major part will be completed and the plotting at least. Okay.
Yes, sir.
Then
Yes, sir.
rest of the portions are okay. Rest of the portions are um, okay. So that is also important, but these two things are very important. So we can also
Yes,
see
sir.
from it, and you can also plot it from that observation table. Okay. Okay. Show me the responses. How is it coming?
Yes, sir. Yes, sir. Uh, Sir, this is the input voltage. It is written, sir,
Yes.
it is V in. This is the gate pulse 1 means the 30-degree gate pulse. For the thyristor 1, this is
Hmm.
the gate pulse thyristor 2 after means 210 degree, 30 degree, 210 degree. This is the output voltage for output.
Output current.
This is the output current. This is for R load and
Mhm.
for
Now, can you please vary the firing pulse?
yes, sir.
Make it
Sir,
120 degree,
yes, sir.
120 degree and 150 degree. How is it coming? Let me check. Sorry.
So it's coming like this. Means
Okay,
at
this is for
the
120 degree. Am I right?
yes, sir. This is means at the point at which it is triggered, the output voltage
Mhm.
is coming and
And
resistive load.
second
So
point also will there. Okay.
yes, sir.
Second trigger is second for next pulse actually. Okay,
Yes,
good.
sir.
Make it 180 degree.
You're getting like this.
180 degree.
Yes, sir.
Uh, 180 degree. Thyristor will be turned on or
It's a means for 180 degree into practical conditions will get very less voltage. Means you can see in the graph, it's from 0 to 0.08. Means the
Hmm.
cut-in voltage types, no, not cut-in
Almost
voltage,
almost zero.
almost 0. And this is in the current also 10 to the power minus 3 point is coming.
Basically, it should not come anything
Yes, sir,
actually.
it should be 0. Yes, sir, I get it, sir. It should be 0.
Hmm.
But sir, I think some
Acha,
practical.
make it 179. Is it possible? Make it
Yes, sir,
179.
I'll do it. Yes, sir, I'll do it. They said it's coming nearly 0, I mean 0.01 and 0 it's coming.
For 179.
Yes, sir.
Okay. Okay. So this is for R load. Okay.
Yes,
So
sir.
show me RL load and RLE load.
So this is for alpha is 60 degree. I have done and
Okay.
I will show the simulation.
How much inductor value you have?
Sir, sir, just it's simulating. I'll.
Okay. Huh.
So taken 0.5.
0.5. Point. Okay. 0.5. Okay.
The results. It's coming like this.
Get pulses based on that get pulses. Okay.
These are the gate pulses.
You are considering 60 degree, am I right?
Yes, sir.
Okay, so make it 150 degree.
Yes, sir. So this is coming.
Current is not there.
Sir, yes, sir. The
Okay. Is it continuous conduction mode? Am I right?
yes, sir.
This is for 150 degree.
Yes, sir. This is for 150 degree.
Okay, good. Achha, now show me RLE load.
Yes, sir. So this is also for 60 degree RL load and the E value is 40.
Just a minute. Okay, 40. Okay, and how much R value? R value and L
Sir,
value?
same, sir. R is 10 and I have taken a very low inductance value, 0.02.
0.02. Okay.
So for that, the graph will be. So this type of graph is coming.
Achha, your output voltage is 40. Then
Sir, first for till the 40 degrees will get the E value that is 40. After
back.
that, conduction starts.
Okay. How much firing pulse you have?
Sir, it's 60 degree.
Achha, and maximum voltage, output voltage is coming how much?
So maximum output voltage is coming. Sir, same, say 100 degree, 100 volt is coming, means the maximum peak value.
100.
Yes, sir.
Achha, so make it 95 back EMF E value.
Okay, sir.
Output voltage, how much?
Sir, less than, sir, little less than 100, that is means it's nearly 97 or 98,
Acha.
and the current is very low.
Current means it is it in discontinuous mode?
Yes, sir, it's discontinuous.
Okay. Now how much firing? 60 degree you have considered, no?
Sir, firing angle.
Huh?
Sir, again, I couldn't hear the question.
How much firing angle you have?
Sir, firing angle, I have, I think 60 degrees there.
60 degree, na?
Yes, sir.
So
Yes.
make it 150 degree. Then let's see what happens.
There's spikes are coming. Means the current is very low, and
Hmm.
voltage is just like a spike, means nearly zero voltage you're getting.
Nearly zero voltage and go to you are using mean block. Am I right? You are using mean block.
Sir, min block means?
There is a mean block you are using. I think so for output voltage. Mean phasor is there, na?
Acha, mean, yes, sir.
RMS. Okay, RMS. How much voltage is coming? 95.
This is, sir, yes, sir, 95 it's coming.
95 means your back EMF. How much back EMF you have considered?
95, yes, sir.
Okay, so almost zero voltage is there for this one.
Yes,
So
sir.
only back
Yes, sir.
EMF is coming over there.
Yes,
Okay.
sir. Yes, sir.
So these kinds of thing you can able to understand. That's why
Yes, sir.
that's
If
the
I'll plot
motivation.
the table. Yes, sir.
That's the
Yes.
motivation. So if you prepare the proper observation table,
Yes,
so
sir.
some interesting factor you can understand means that kinds of factors are not written in the book. Okay, so that you can realize from the simulation. So experimentally, all kinds of things we are not able to study for
Yes.
experimental setup. So that's why the simulation platform is there. How the system is behaving we changing of the parameters in control system terminology you can say like that is called identifications. Okay, identifications of physical system for physical systems. Okay, so you can understand the dynamics identifications of the dynamics of the system. Good. Okay,
Yes, sir.
so you please complete your report. Okay.
Yes, sir. I'll do it. Yes, sir.
Okay, so after that who want to show their simulation next want to show me the simulation.
Sir, I can show the simulation.
Mahesh, show me. Okay,
Sir, I think
so
the screen is visible.
yes, your simulation. I can see your simulation. Okay, so one by one, you please show me.
Okay, sir. Sir, I have taken the single circuit and you just switch to shift between inductor and power battery source so that in one circuit, like we don't need
Good,
multiple
good.
circuit to do that.
Okay, okay. Very
Sir,
good.
so for R load, this is asymmetric converter, and I'm simulating. So this is the graphs are coming. This is the current graph.
Current wave from okay. How much current value? Average is it in discontinuous mode? I think so.
Yes, sir.
Hmm.
And this is the voltage that forms. In 60-degree angle side it's coming.
Hmm.
And if we'll use the inductor, then
Acha, Mahesh, can you please tell me one thing?
then
Is there
spikes are more.
any changes? Mahesh, am I audible?
Yes, sir. Yes,
Can
sir.
you can you please tell me one just simple thing? Is there any difference in the simulation of asymmetrical bridge and symmetrical bridge?
Sir, yes, sir. In asymmetrical bridge, like in voltage and current waveforms, sir, you are asking, or like these are the
No,
symmetrical bridge?
from point of view, I'm asking you. Okay. The topological point of view, different. Okay, no problem.
Okay, sir. Sir,
From
in waveform that I
from
have observed, like in voltage, the spikes are coming like in the below in case of symmetrical, but
not
in case
about
of
the spike. Okay, not about the spike. Spike actually coming due to in multi-sim what happened? Some inherent problem is there. Suppose the spike, what kinds of problem? I'm just clarifying the problem. Okay, so exact parameter selection is needed for that multi-sim. Otherwise, some simulation error is not coming, but this unnecessary spikes will be there. Okay, so here what we are doing, we are changing the parameter value continuously. Okay, for individual simulations. So spike is not our main concern. Okay, spike is coming, but we are overlooking some of point of view. Okay, but ringing effect that we can see. But my point is that, can you please compare for asymmetrical bridge results and symmetrical bridge results? So in voltage waveform point of view, in current waveform point of view. Okay, so both are same or both are different? Did you see it?
I am finding both are same.
Both are same. So what is the advantage for what is the topological advantage?
Sir, in symmetrical and sir, in case of asymmetrical, we can use the freewheeling diode. So average, we can increase it.
We can.
Increase the average value, we can use a freewheeling diode.
Okay.
But that's, I think, not possible in case of symmetrical.
No, actually, what happened for symmetrical, asymmetrical, basic differences are there. For you need to, if you plot the both the voltage waveform, you can understand. Okay, so first, okay, so let's see. Okay, do you have the simulation of asymmetrical bridge with you
Yes, sir.
and symmetrical bridge? Both you have.
Yes, sir.
Open a file. Okay, open करो एक file open करो. Open a file. New
Sir,
file.
new multisim file or
New file. Okay, make a new sheet actually. Now copy करो. Okay, copy both the simulations. Control A, Control C, and Control V. Yes. Another one.
in the same?
Same. Now I think name need to be changed. Am I right? Nah, names are automatically has changed. I think so.
Yes, sir. Automatically based.
So now what you are doing, go for RL load. Okay.
RL.
RL.
Yes, sir. It's RL. RL
Ha,
same value I just need to put.
ha. Same value you make it.
Yes, sir.
Inductor value same. RL load. Okay.
Yes, sir.
Then one scope you please fix a bit where both of the converter voltage will be there. Okay. And then same oscilloscope it is not able to see. If you take a oscilloscope, you are taking multimeter actually.
Okay,
Take
sir.
an oscilloscope, yes. Okay, where both the voltage will be there. Then to visualize the voltage actually, nothing else.
So simulate.
Yes, yes, simulate करो and grapher view में देखना है. Okay, please simulate it. Open that oscilloscope. Let me check. Go to grapher and make it auto scale. That voltage are different, so it is 10 millivolt per division though, so you make it 50 volt, sorry, 10 volt per division, 10 or 20 like that, you make it 20 volt. Yes, another one is make it 20 volt per division. No, 20 volt. Now shifting, this shifting is required, position changings are required.
Yes, sir.
Go to grapher mode. Okay, go to grapher mode. Acha, this is 50 volt and 20 volt. Make it 50. Both voltage range should be same. Go to grapher mode. Position changing option is not there. Y position. Change in
Yes.
Y position. Yes, changing Y position. Below karo minus. Okay. Now stop the simulation and go to grapher mode. Grapher view. Auto scale karo, Y axis. This is for 60 degree. Am I right?
Yes, sir.
So negative voltage spike is there. Okay. Acha, make
Yes,
it.
I got, I think, for first graph, like it is starting above 0, but in the second graph, no, we have shifted the graph.
I've shifted, nothing else.
Hmm.
Make it more firing angle, make it 120. Let me see.
Okay.
And inductor value को high करो. Make it make the inductor value. You are considering 0.05, तो make
0.1.
1 Henry, 1 Henry, 1 Henry, 1 Henry.
Firing angle.
Firing angle 60 degree. Okay, keep it 60. Then let's see what happens.
Okay, sir.
Okay. So you are right. So both are same.
Yes, sir.
So now make it 120 degree or 150 degree firing angle.
Different.
So conduction time is less. Okay. Okay. So for RLE load. Good. For RLE load.
Okay, sir. It was in RLE only.
Okay, it was RLE, no?
Yes, sir. Now I'm simulating for RL.
Okay.
Last time the switch was on. This is for 150 conduction angle.
Hmm. Hmm. 150. So voltage value is very less.
Yes, sir.
Hmm. So current may be in discontinuous, I think so. Okay. Now show me the current waveform, both the cases.
Transient.
Or you can add some current probe to show the. Okay, you whatever you feel easier, you can go.
Simulation coming, I think.
I think simulation time is very less.
Huh. Okay.
Or you can use the current probe also. So I think it is not reaching the transient. It is in transient condition. It is not reaching the steady state value. So you can also use the current probe. That right side lower one you can see over there. Lower one, last one, last one. Yes, current probe. Take it. So scroll up karo. No. You have to insert a clamp meter. No, this is a clamp meter. So
Yes, sir.
so wire should pass through that meter. So you put it in just above of your wire actually. Then it will be green actually. If you put it, so it shows green signal.
Not getting.
No. That circle should be put above the.
Uh,
Yes. Now it
the
is right. And backside will be
higher,
connected.
therefore it is coming like that.
I'm not getting what happened.
In the inductor value is higher, like 1 Henry. So therefore, it is big, and the
Taking
current is
losses
not
to.
saturating within that time.
Yes, sir.
So we can take 0.01, so it will saturate and graph will be okay.
Okay, then let's see. Otherwise, we can also see from current probe also. If our inductor is more, then what happened with us? So, okay, you make it that one, no issue. I don't have any problem. Now it is coming discontinuous mode.
For inductor value change, so it's coming discontinuous.
Hmm.
Like 0, 1. Yes, sir.
Hmm. Okay, so it is settled down 300 milliampere. Okay.
Yes, sir.
Acha, that current is linear different, right?
Sorry, sir.
Both are any shifting is there. I have observed current shifting.
Yes, sir. The average
Okay.
value, mean value is shifted, sir. Right?
Okay, good. ठीक है, so simulation is okay. So do you prepare the report?
No, sir. I have taken all the screenshots and the graphs. I have to only compile it and make the report.
Okay, okay, complete it. Okay.
Sure, sir.
Complete it.
Thank you, sir.
Thank you. Okay, so any other student want to share the simulations? Anyone? No one is interested to show their simulation. What happened? Anyone is not interested? Vishwajit?
Yes, sir.
So there are two Vishwajit, am I right?
Yes, sir.
In your class, Vishwajit Jogdev, another
Actually, 3.
three.
Sir, there are
Vishwajit
three.
Mishra, Vishwajit Patnaik. Am I right? Three Vishwajits are there. Am I right?
Yes, sir.
No one is interested.
Sir, I'm sharing my simulation.
So you are Vishwajit.
Vishnu Mishra.
You are Vishwajit
Mishra.
Mishra. Good. Show me Vishwajit.
Is the screen visible?
Your screen is visible, but simulation is not visible. Yes, it is coming now.
Okay. So this is symmetrical R load.
Show me the waveform. Yes.
Yes, sir. So uh, this is the input and this is the gate pulse.
Okay.
This is the output, 60 volt, 60 degrees the firing angle. So this is the output and uh, this is the current. R load, the voltage is current is following the voltage of.
Okay.
This
is for R load.
Yes.
Acha.
This is yes.
RL load, no?
This is R load. This is RL load.
Okay.
This is the input and gate pulse. And this is the output and this is the current.
All are in 60 degree. Na? Can you please make it 170 degree?
Yes, sir. The zero, nearly zero.
Let me check.
This
Almost
is milli,
zero,
in milli, 20 milli.
some portion is zero and okay. So discontinuous mode. Okay. This is current waveform or voltage waveform?
This is current waveform. This I have made it auto zoom, so this is like coming. The value is peak is nearly 20 milli.
Milliampere. Okay.
Yeah.
Maybe very less. 20 milliampere.
Yes.
Almost zero. Okay. Good. Okay. So now go for that RLE load.
So this is the I for RLE load. Yes. So this is the
Current waveform and gate pulse.
This is the gate pulse and input voltage. So and this is the output voltage. So this is the E during the discontinuous. This is the not where the current is not there. So this is the output voltage that is equals to E. And this is the current waveform. E is taken as 40 volt.
40 volt, no?
Yes, sir.
But current is in discontinuous mode.
Yes, sir.
Okay, so make E around 150 volt.
Input is 100, sir.
And then let's see what happened. Nothing is coming, no?
No.
Yes. So peak is almost it is input 100 means peak is how much?
141.
100 into root 2. Huh? What happened?
141. 141.
So it is now around 150. So no, nothing is there. Good. Okay. So now make the fire, change the firing angle.
Input is
Change it. Then make it 100 and now changing the firing angle. Make it 90 degree.
this is the 100 volt is E is 100. So when current is not present, so the output is 100 volt, and this is the current.
Okay. Make it 150 degree. Okay. Not coming. Money. Turned off. Okay.
Because
It's not
the E is 100, therefore.
yes, it's crossing that 100. Okay.
Yes.
That's okay. Good job. Do you prepare the report?
Sir, I have prepared the. I have not completed the report. I have completed the tables. So
Okay.
I'll complete it and share.
Okay. Okay. Good. No problem. ঠিক আছে বিশ্বজিৎ, good job. Okay, so you please see I'm sharing some material to you, like fourth experiment, fourth simulation is completed. Am I right? Up to fourth has been completed.
Yes, sir.
Yes. Is my computer screen is visible from your end?
Yes, sir.
Okay, so single phase, all kinds of simulations for single phase. Okay, we have almost completed. Okay, so now we are going to switch for three phase. Okay, so just for a moment. You please check. Do you receive the material what I have posted over there?
Yes, sir.
Good. Okay. So three phase. So same kinds of thing. Now we are going to perform for three phase. Okay. Same kinds of thing means single phase we are doing for uncontrolled and controlled. Okay. So similarly, same thing for three phase we can go. So what is the motivations for changing from single phase to three phase? The important motivation is that ripple factor. Okay. So ripple factor means ripple frequency. Okay. So for three phase, what happened in single phase when we are converting from uncontrolled, sorry, when we are rectifying the from AC to DC, then main problem is that we are only changing the pulses. Okay, that how much frequency you have. Okay, if it is 50 hertz signal, so in AC when it is we pulsating DC. Okay, in AC it is 50 hertz. When it is pulsating DC, so you'll get 100 hertz. Okay, so what happened? Basically, that if you see the DC having some pulsating with two pulses. Okay. But in case of three phase, what happened? You can see that in the same durations, okay, suppose 180 degree we are considering, okay. So you can see that all the signals are 120 degree apart each other. Okay, now if you converting that AC to pulse DC, so inherently the ripple frequency will be increased. That is number one benefit. So that if you want to design, if you want to incorporate some input side capacitor, okay, for single phase AC, it will be more value, okay, compared to your three phase AC. Okay, so when you are comparing to converting the three phase AC to pulsating DC, so how much capacitor values, input capacitor values required, it will be less. Basically for what? If you want to smoothing them, okay. So as the ripple frequency is more for the pulsating DC for three phase, so the capacitor value going to be less. Okay, the costing will be one important issue. This is first factor. Second factor is what? The average output voltage. Okay, compared to DC, if you can see that average output voltage will be more. Okay, as well as the utilization factor. Basically, our generation is happened in three phase. Okay, if we are going to convert them three phase to single phase, or you know that from the start configurations. Just for a moment. Sorry for that. Okay, so now we are going to discuss about the three-phase full wave. Okay, three-phase full wave for diode. Okay, and diode for uncontrolled and for controlled rectifier. So full wave is there as well as half wave you can also do. Okay, so that you can also do, but we are directly going for full wave. Okay, so you see that basic theories are there. Okay, for diode rectifier, so it is neutral clamp. Okay, that we are talking about utilization factor. Okay, so three phase generation is that for balance load is good. Okay, otherwise if you want to go for single phase, so neutral point you need to find out, then you will get the single phase, then you can implement it. Okay, that's the issue. Okay, so here you can see that how much that values are there, root 3 VM. Okay, that VCA, so line voltage you can see over there. Okay, so durations, output voltage duration, some basic diagrams are given. Okay, so that portions are already there. So if you want to, there is a leading 30-degree leading is there. Okay, so phase to line conversion is there. So 30-degree leading is there. 0 means 30-degree. Okay, so like that way, so you have to calculate the firing pulse. Okay, so average output voltage, RMS output voltage, the basic things are already given. So now the basic simulations. Okay, so for the basic simulation, that phase voltages are there. Okay, directly you will get it from here. Okay, some probes are there, input probes are there, from here directly we can calculate. Okay, MUR460 diodes are given. Okay, so how the waveforms are coming for different that parameters are given from that table, it's there. So parameter value you can easily get it. So output currents, okay, sorry, output voltage, from here you will get the output voltage. So you can see previous case how much you are getting for 100. So you can see over there average voltage is more than that. Okay, if you compare with your single phase, so you can see that average voltage is more than that. If you compare the pulsating, if you compare the ripple frequency for single phase pulsating DC and for pulsating DC for three phase, you can see that 3 times. Okay, 3 times more than ripple frequency is 3 times more than your single phase. Okay, single phase rectified DC or pulsating DC. Okay, so ripple frequency is more means so lesser value of capacitors are required. So costing will be less. Okay, but voltage is more. So voltage level also be an important issue. For this case, normally what happens? It's not a huge changes of the voltage. Okay, still it's good changes of the voltage, but voltage level will be more. The capacitor. Okay, but capacitor value will be less. Load current you can also see. Okay, so for inductor, so no need to write the small inductance. Okay, so small inductance also okay, but in terms of your rated one, suppose rated one is 1 Henry or 0.1 Henry or 0.01 Henry. So 0.1 Henry, that 0.001 Henry is small compared to that one, but 0.001 Henry inherently very small inductance. Okay, so no need to write that small inductance high inductance. So you can write that changing of the inductance. So you can see their responses. This is for uncontrolled. Okay, some waveforms you can also see over there. Now we are going for that controlled one. Okay, so variations of the firing pulse, same type of observation you can see. Okay, so now we can go for that full control. Here. Okay, thyristors are there. So there, here you can see the pulse trade you are given. So, shifting is there. Okay, based on the shifting, you can see over there how much the voltage waveform, current waveform. So you can see voltage waveforms are there. Okay, so for the duration, you can see 3 cycles are there. Okay, within 180 degree. So 3 cycles are there almost. So variations of the L. Okay, so observation tables you can also prepare for it. Then RLE load. Okay, Okay, so now you can change the firing pulse and change the inductor value. Okay, as well as E value. So you'll get some defined waveform. Then finally observation table you can also find out. So all the columns must be there. Okay, I hope all of you are able to understand. Is there any query from your end?
No, sir.
Okay. So no queries from your end. Good. Okay. So okay. So I hope all people